As software engineers, there are many things we are never supposed to do. Among these, of course, is rewriting something that already exists, failing to reach for a tool that has already been written and tested. But ironically, this is one of our favorite things to do, to go and needlessly reinvent the wheel over and over again. And so I'm going to begin this talk by doing exactly that, by rewriting something that surely has been written altogether too many times already. I'm speaking, of course, of a wrapper for a POSIX file descriptor, something that can take and abstract away all of the difficulties of interacting with this C-style API. Of course, if we don't actually hold a file descriptor, the entire construction is useless, and so we start therewith. But it's private, and so the onus is now on us to fill it in. We author a constructor which does exactly this. Doesn't just fill in the file descriptor, of course, but abstracts away one of the things that bites so many people in C, the requirement that you manually check the return code at every time that you invoke a function. We abstract that away and solve that problem one time. But there's another problem people run into often with C-style APIs. They get the resources that they want, and then they simply forget to dispose of them. But C++, of course, has an answer to this as well. We have a destructor in which we can call close to dispose of the file descriptor. But simply acquiring and releasing resources repeatedly is of no use whatsoever. It just wastes cycles. We need some actual purpose for which we want to use this file descriptor, useful functionality that is exposed by this class. And so we enrich it with read_sum, which accepts a buffer of bytes, reads into those bytes, and returns the number that were actually populated. Once again, we are abstracting away the kind of error handling that is error-prone in C code, but which C++ allows us to concentrate in exactly one place. But as we look at the class we've just written, as we thought about the functionality we've made available in idiomatic C++, we realize something. All we've really written is scaffolding. All of the interesting functionality you can accomplish with the code on this slide is vended to you by these functions from glibc. And so if you want to figure out how these interesting operations are actually performed, maybe you open up these functions trying to see how you actually achieve opening a file descriptor, closing it, and reading some bytes. But if you do that, of course, you will be disappointed once again, because inside of these glibc functions, you are just going to find a syscall, because the functionality they expose is not something you can access from user space. You need to go and ask the kernel to do it on your behalf. You need to marshal some arguments and then transition into the kernel and allow the kernel to make forward progress instead of your thread, to wait for it to be done. Once the operation you requested has completed, the kernel marshals the results thereof back to you, allowing you to resume. But what if we don't like this formulation? What if we don't like the idea that our thread simply waits until one operation is completed? What if we want to make better use of that resource? What if we want to use C++26 to write an asynchronous version of our read_sum function, one which returns a sender, one which reads bytes without consuming an entire thread for the duration of the operation? But this, of course, raises the question of what is a sender. And while this is not an introductory talk to std execution, I think it's useful to explore an analogy, one that we're going to use over and over again throughout the remainder of this talk. An analogy, of course, that is grounded in regular synchronous functions that we all understand. We all write regular synchronous functions every single day. But when we do that, we understand that a regular synchronous function is not useful on its own. You write a regular synchronous function and you compile it, and then it is realized as some instructions in the resulting program. But if those instructions are never executed, if that function is never called, the function is completely useless. And so our ecosystem that a function call participates in, of course, has a call site, somewhere someone decides they want to call a particular function with some arguments. But this selection of a call site is insufficient. The function, of course, needs to have variables with automatic storage duration, local scratch space it can use to achieve its ends. And so when we bring a call site and function together, we obtain a stack frame. But this is just data layout. If we actually want to do anything, we actually need to take an execution agent and allow it to make forward progress on the function. We need to jump into its body and allow it to execute, ending with a return to the call site. Having had this not only explained but also demonstrated diagrammatically, we're now ready to understand the analog in the asynchronous domain. We're ready to understand how senders and receivers model this problem not synchronously, but asynchronously. At the center of the ecosystem, we have a sender, an analog to our synchronous function. And once again, a sender just represents latent asynchronous execution. It does nothing on its own. It requires cooperation from something else in the ecosystem. It requires that it be brought together with a receiver, that it be connected thereto. This is the moral equivalent of selecting the call site from which you call a function in the synchronous domain. And in bearing out this analogy, when you connect a sender and receiver, you obtain out the other side an operation state, the asynchronous analog of a synchronous stack frame. Stable local storage solely for the asynchronous operation that will be in flight, but is not yet. Because unlike in the synchronous domain, allocating the stack frame and performing the invocation are not married to one another. You can create an operation state and decide that you do not want to make forward progress on that operation yet. And then later you decide you want to commit to that asynchronous action. You come and you call start on that operation state. An asynchronous operation results. An asynchronous execution proceeds until its completion, whereat a completion signal is sent to the receiver, thereby closing our loop in the asynchronous domain as well. But as compared to synchronous functions, senders have an interesting property. Because senders aren't just the analog of a synchronous function, they are the asynchronous analog of a fully curried synchronous function. Senders are not awaiting the selection of any parameters, they are fully parameterized. We could say that they are the asynchronous analog of a nullary function. And so if we want to start understanding the part of our ecosystem occupied by a sender, we can return to our read-sum function. A read-sum function which binds together invocation and selection of arguments. The exact instant at which you bind arguments into this function is the exact instant whereat you are committed to make forward progress thereupon. But we don't need to structure our function this way. We can make it more similar to the senders and receivers ecosystem by making it a higher order function, one which accepts a parameter and then binds it into a nullary invocable which it returns, allowing for the separation of the concerns of selecting arguments and committing to the actual execution represented by whatever is returned. And so now we can take this and transform it one more time. Transform it to the asynchronous domain and see that we return a sender. This function now has the same role as the synchronous function we just saw. It takes the buffer and it binds it into a sender, but doesn't commit to any forward progress. It simply returns that sender to be consumed by the caller when and if they decide they want to make forward progress on the operation represented thereby. And if you want to know more about senders and receivers and how to write algorithms therewith, boy, do I have a watch list of talks for you. But if you've seen these talks, if you've seen particularly the one in the top left, maybe something is bothering you about the formulation on which I am setting out. Because in this talk, I bootstrap a C++ networking stack and asynchronous C++ server from nothing using senders and receivers. And surely in doing that, I went and wrote read-sum, so isn't this formulation we're starting this talk out with duplicative thereof? But in that talk, I used epoll. I used epoll to realize asynchronous operations, and epoll is a readiness-based model, which means that to perform an asynchronous read, we first need to go to some epoll file descriptor and tell it we're interested in reading from some other file descriptor. But this is just an expression of interest. Epoll doesn't tell us if we can actually read from that file descriptor. The read is not actually performed. Instead, we need to perform another syscall in order to wait for the file descriptor to be ready to perform the corresponding operation. But in doing this second syscall, we still haven't read anything. We've just had the kernel notify us that if we want to, we could read now. And so we make a third system call to actually finalize our asynchronous operation. We actually perform that read. And in so doing, we are accepting a performance overhead as compared to the synchronous domain. We now make between 1 and 3 syscalls in order to perform our read instead of just 1. And if we're not happy with this, we can go to the Linux man pages. And we find that Linux supports another way to submit asynchronous syscalls. Linux supports IO uring, which despite the name, despite the title in the man page article here, is not just a way of accomplishing IO, it's a generic asynchronous way of submitting syscalls to the Linux kernel. Which of course raises the question of why I didn't deal with this problem in that first talk I was referring to. Why did I go ahead and use epoll? And at the time, I justified this by saying that the kernel that I had access to was simply too old to support IOU ring, and so I was left only with epoll. But fortunately, in the intervening time, I have figured out how to upgrade my kernel, and so now we're left trying to figure out how we can bootstrap read-sum in the domain of IOU ring. Which means, of course, we need to understand IOU ring, and so we start at the beginning, where we bring an IOU ring into existence by performing the IOU ring setup syscall. This returns to us a file descriptor that you can, of course, use as a handle to that IOU ring. But you can also use it for something else interesting. You can pass it to mmap. You can mmap into your process regions of memory which you share with the kernel. These are the rings to which the ring in IOU ring refers. And so after you perform this syscall successfully and perform those mmaps successfully, you end up with something that looks like this. A submission queue or submission ring, and a completion queue and completion ring with the kernel sitting in the middle. But if we actually want to use this, we need to figure out how to form submissions, how to get the kernel to look at these rings and do work on our behalf. And so we start with the structure we deposit in the submission queue that we place in the submission ring, an SQE or submission queue entry. And because so many syscalls are supported, you can see the structure of this is quite complicated. But I want to draw your attention to the bottom, to user data. That allows us to leave behind a unique token, which the kernel will pass back to us, which allows us to link a completion with this submission. Once we figure out how to populate this submission queue entry for our syscall, we, of course, deposit it in the submission ring. But the kernel's not obligated to look at this memory all the time. We need to go ahead and ring a doorbell to let it know work is pending. And so we ring the doorbell by calling either IOU ring enter or IOU ring enter 2. We tell the kernel that there is forward progress to be made on the IOU ring, that it should go and pull in those submission queue entries. And once it's pulled in those submission queue entries, now in the background, the asynchronous syscall is in progress. It's making forward progress until it completes, and the kernel tells us about that by leaving a completion queue entry behind in the completion ring. And so we review that structure as well. Far simpler than the submission queue entry. In the same way, the parameterization of the synchronous syscall function is far more complicated than the single integer returned therefrom. At any rate, now that we understand this ecosystem, we have to go figure out how we're going to realize it in C++. And so once again, we write a class that abstracts away all of the complicated interop between a C-style API and a C++ one. But this doesn't close the loop on our file descriptor. This doesn't render our file descriptor aware of our IOU ring context. And if our IOU ring context is to be the locus of asynchronous forward progress, then surely our file descriptor's interface should be aware of it. And so we go and we enrich that interface. We accept an IOU ring context to the constructor, and we store it in a reference member so that throughout the lifetime of this file descriptor wrapper, we have access to a context we can use to make asynchronous forward progress. But this is just low-hanging fruit. We all know how to pass a reference to a constructor and populate a member therewith. What's far more interesting is what we're going to write in this function. How are we actually going to obtain a sender which, if connected and started, goes off and performs a syscall via IOU ring to read bytes from a file descriptor? And so we turn our attention to that. We turn our attention to what code we can possibly write in this function. And given that it needs to represent latent execution and return a sender, we suppose that the body contains a return statement. And this is borne out by reality, but what do we return? We want to use our IOU ring context to submit a syscall, but what exactly is the parameterization thereof? And so we take a step back. We take a step back and think about our introduction to IOU ring. We think about the phases of making an asynchronous syscall. Of course, we have to start by obtaining a submission queue entry, something we can fill in and pass through to the kernel. But simply obtaining this memory doesn't actually parameterize it. We need to go and fill it in with the information the kernel needs in order to make forward progress on the particular operation we want to perform. Then, of course, with that done, we need to submit it to the kernel, which leaves us simply waiting for a completion queue entry to be posted back to us. Once we receive that completion queue entry, the operation is finished, and so from our syscall sender, we should, of course, complete the operation. But as we think about these 5 steps, we realize something. We realize that all of these 5 steps, except for one, are common. They're performed equally and identically for every syscall. The only one that varies is exactly how we populate the SQE in order to tell the kernel what it is we want to do. And so as we go back to that function we're trying to fill in, we find this borne out by the interface. We parameterize syscall with a single invocable, which accepts an SQE reference and has the responsibility of filling that SQE in with the parameterization of the syscall it wishes to perform. And so, of course, we have to do that. We need to set up the SQE to perform a read against a certain file descriptor into a certain buffer of a certain length. But if we think back to when I introduced IOUring, we recall something. We recall that IOUring doesn't output to us a size t, it outputs a CQE. And so if we want this interface to be isomorphic to the one we were providing in the synchronous domain, we need to obtain the CQE that's output from the syscall and transform it somehow. We need to use a combinator from std execution to attach a continuation to our asynchronous operation. We need to do something afterwards with that CQE. And of course, the first thing we do is once again abstract away that error-prone C error checking. We check to see if the result is less than 0, and if it is, we throw an exception. But the embedding of this throw is special. We're throwing an exception from a function being invoked by std execution then in the middle of an asynchronous pipeline. When we throw that exception, the implementation of std execution then will catch it. And because std execution's asynchronous model is totalizing, because it only permits asynchronous modalities of completion, std execution then's implementation will catch that exception and send it downstream as an erroneous asynchronous completion out of the operation we're authoring. But what about the happy case? What about when the read succeeds? We go and we cast the result to a size t and return it, then causes that CQE result to be coalesced to a size t, and so we have finally provided the same higher level interface in the asynchronous domain that we provided earlier in the synchronous one. But in so doing, we've raised another question. We wrote this code and now we have filled in code for a function we didn't know the implementation of at the beginning, but we've seen another function whose implementation we don't understand. We don't know how it is that syscall is implemented, and so we go to thinking about that. And in thinking about this shared code, we think back to that list I showed earlier. We think about those common tasks that now we're abstracting away into this function. And so we imagine that we go and we get an SQE from the SQE ring. We call the user-provided invocable, and then we return a new sender that consumes the SQE and awaits for its completion. And as you stare at this slide, something may bother you. What may bother you depends on how much std execution you know, but at the very least, I think it's bothersome to everyone that we are just blindly dereferencing this null pointer. Why are we getting back a pointer if we know it's never null? But on the other hand, we're just getting introduced to IOUring, so maybe it's the case this pointer can never be null. And so we return to our formulation of IOUring. We return to our understanding thereof. We know that we leave behind an SQE to tell the kernel what to do, but the fact that we're using a ring and not a single region in memory implies that we can put other SQEs in here. But of course, the kernel is going to consume those SQEs, but there's no reason to believe the kernel is faster at consuming them than we are at producing them. Maybe we're actually really, really good at producing SQEs, and when we go to find a slot to perform a new submission, there is no slot to be had. And if you look at the implementation of getSQE, this is actually borne out thereby. You can see we go and get the head and tail of the ring. We perform the needful mask in order to wrap to a linear index, and then we check to see if the ring is full. If the ring is full, we return null putter, but the code we saw on the preceding slide will simply dereference this null putter and run afoul of undefined behavior. And so maybe a better thing we can do is we can reformulate this interface to be safe. We can reformulate it so that instead of returning an error-prone pointer, we return a reference. We wait for an SQE to become available, and then we consume it without involving problematic pointers, without the specter of a null pointer dereference. But there are still problems with this formulation. And the first one I want to start with seems aesthetic at first, but later in the talk you'll understand that it's critical. And that's that the sender factory we just authored is an eager API. When you call the factory, you don't just get back a sender, there are side effects. It goes and gets an SQE and then calls the prepare function and then returns the sender. But when we introduced senders and receivers, we talked about how a sender was a latent encapsulation of asynchronous execution. But we can easily solve this. We simply go back to our code and we slightly re-indent it. Now that it's slightly re-indented, we can simply wrap it up in the appropriate asynchronous wrappers, and now we wait until the operation is started in order for us to wait for an SQE. Sequence is a combinator from NVIDIA's studexec library, which just runs one asynchronous operation after another. And so asynchronously, when that sender is eventually connected and started, we're going to wait for an SQE, and then we're going to invoke prepare. Immediately thereafter in our asynchronous sequence, we're going to consume the SQE. But there's still a problem. And the problem is this is a blocking API. And there's an aesthetic problem with this as well. The aesthetic problem with this, of course, is that you walked into a talk called Towards Async Everything, and so it would be untoward if in the first 30 minutes I threw a blocking API at you. But just as our first aesthetic concern has something borne out by a problematic consequence thereof, so too does a blocking API. There is a deep problem in using a blocking API inside of an asynchronous pipeline. It is overwhelmingly likely that our IOU ring is only safe to interact with from a single thread. It's asynchronous, but it's not thread safe. And so that suggests to us that if we are on a thread that is interacting with the IOU ring by waiting for an SQE, it is doing so at the exclusion of other threads. Because it is waiting for an SQE, no other thread is interacting with the IOU ring. Particularly, no other thread is calling IOU ring enter in order to ring the doorbell and cause the kernel to consume SQEs and make an SQE available for us. And I don't need to just describe this to you. We can actually look at some code that behaves this way. We construct an IOU ring context, and then we connect a syscall sender to some unstated receiver. Note that what we get back is an operation state, a representation of asynchronous execution, which is fully formed, but which is not yet making forward progress. In order to make forward progress, I need to call stood execution start thereupon, but think about what happens internally. Sequence calls just. Just immediately completes and passes through control to then invokes that lambda, and then we call wait for SQE therein. But imagine that when we call start, the IOU ring context submission queue is already full. If it's already full, then we need to call IOU ring enter in order to cause entries to become available. But we know from this description, from this example, that we are now blocking inside of the line of code directly above IOU ring enter. We are deadlocked, waiting for a condition that will never occur because our current action is occurring at the exclusion of what we are waiting for. But this synchronous blocking formulation is so simple. It was so beautiful and elegant. And I would posit that the reason for this is not endemic to the synchronous domain, at the exclusion of the asynchronous one, is because so many things are taken away from us, abstracted away from us in the synchronous domain, that we have to surface explicitly in the asynchronous one. Let's walk through at a low level what happens when we call wait for SQE. We probably issue a call instruction in order to call that function. This leaves behind on the stack the return address. When that function finally has obtained an SQE and wants to go back to the caller, it uses the ret instruction to do so, which pops this instruction pointer and returns thereto. This, of course, is complexity we have to surface directly in the asynchronous domain, but let's look at this diagrammatically. Let's think about what's actually happening here. We have some caller and they want to wait for an SQE, and so they call wait for SQE. The arrow points from wait for SQE back to caller because wait for SQE has a return address that points at the caller. Now it is incumbent upon wait for SQE to figure out how exactly it's going to wait for that SQE. Maybe it elects to do this by falling asleep on a condition variable. Falling asleep on a condition variable, resting assured that some other actor in the system at some time later is going to realize SQEs are available and call notify one or notify all on this condition variable. And note that we're not limited to just one task waiting on the condition variable. It can fan out and we can have many tasks waiting thereupon. But think about part of the formulation I just gave you. I said that wait for SQE has a pointer back to its caller. But we can actually look at the caller of wait for SQE. We know exactly where it's being called from. But do you really think that return address pointer is pointing back to this entire function? No. It is pointing back to the exact instruction it has to perform after the call for wait for SQE. It is pointing to exactly this part of the function. And so what we're seeing is that continuations exist in the synchronous domain as well. It's just that the compiler abstracts them away from us, and so we have to never look at it. Let's go and see how we can make the same diagram in the asynchronous domain. We now have some continuation which gets provided to an asynchronous operation called wait for SQE. Wait for SQE, of course, has this continuation, but now wait for SQE needs to figure out how to wait asynchronously. Because it needs to wait asynchronously, it cannot avail itself of a condition variable because a condition variable is a blocking form of waiting. But think about the ecosystem we're in. We know that every single asynchronous operation in std execution has an operation state. We know that an operation state is just a C++ type. And we know it remains valid for the lifetime of the asynchronous operation in the same way that a synchronous function stack frame remains valid for the lifetime thereof. And so we can simply enrich our operation state. We can add to it an intrusive linked list hook, and it can go to sleep by just adding itself to a linked list, resting assured that someone else somewhere in the system will notice SQEs become available at some point and wake us back up. And just like the condition variable formulation, we can fan out on this as well. We can trivially fan out on this because every first-year computer science student knows that linked lists can have more than one element. But there's a problem on this slide as well. The problem is in those blue boxes. What I've done is I've used a technical term for the thing that gets invoked when we complete our asynchronous operation. I've called it a continuation. But in the senders and receivers ecosystem, we don't call it a continuation. We call it by the name of the entity in the ecosystem which models it. We instead call it a receiver. And so now all that remains is actually backing this up with code, surfacing this in code that we can actually execute, and so we get started. We have an abstract base class that has a complete function which can be invoked when an SQE becomes available. And then, of course, we have that intrusive linked list node. And if the virtual function here is terrifying to you, just think to what happened in the synchronous domain. We left behind some address, and then we jumped back to that address when the function was done. Here we have a virtual function, and it's simply dispatched when the function is done. But that jumping back to a function means we're jumping to a concrete function in the synchronous domain, one that return address takes us to. And so we have to stamp that out by providing our wait for SQE operation state, which derives from this base class and surfaces this functionality by sending set value through to a receiver. This formulation is identical to us returning to a function that we actually know once we go through the dispatch. Once we jump to the return address, we're in a real function, a function we actually know. And so to here, when we call complete, we go what we call a real function, a receiver that is modeled in the C++ type system as evidenced by the fact that we accept it as a template argument. But this formulation is not working code you can run. Operation states have a basis operation called start, and that is not on this slide. An operation state probably also needs a constructor so we can bring it into being. But we know that senders and receivers are connected to form an operation state, and we haven't seen a sender for this operation. And idiomatically, we typically surface senders via a sender factory, and we haven't written one of those either. But it would be kind of tedious to bootstrap all of that boilerplate every single time we want to surface this pattern, one which I hope you will conclude by the end of this talk comes up frequently. And so what we should instead do is we should surface this through an algorithm in the idiomatic way we do in the senders and receivers domain. And so we go and instead of having a wait for SQE base, which is concrete to the exact operation we're doing, we have an externally completed base, which is now generic. Asynchronous functions in std execution surface their completion modalities by instantiating the std execution completion signatures class template. And so we provide an instantiation thereof to this base class, and it stamps out a complete overload for each and every completion modality. It erases every single way in which we want this externally completed operation to complete. Externally completed, of course, refers to the fact that we want to capture a completion which is delivered outside of the std execution ecosystem. We want to tame it by delivering it there through. But simply having this base class doesn't get us anything. We actually need that algorithm. We need externally completed. We provide it with the signatures we want to complete with, and then we can customize the base class for reasons that are going to become apparent in just a moment. But how does this algorithm work? What does it actually do mechanically? What value does it bring to us? And we see that it accepts an initiation which accepts a base reference as a parameter. But we also know it's a sender factory. We know that sender factories are lazy. And so all this does is take initiate and curry it into a sender which it returns. But at some point, in order to make use of a sender, someone needs to connect it with a receiver to form an operation state. And externally completed makes that operation state derived from that base class, thereby providing a stable instance thereof for the duration of the asynchronous execution. Asynchronous execution which has not yet begun, because we just connected a sender and a receiver. We didn't yet call start. Once start is invoked, externally completed's operation state invokes the initiation function with itself. Now that initiation function has a vtable it can dispatch to. It has a vtable it can dispatch to complete the operation, and so it goes off and does whatever is necessary to glue that external completion in. But there is still a problem with what we see on the slide. There's a problem with this part of what we're seeing on the slide, because we've presented the externally completed algorithm as a regular C++ function. And it's 2026. No one writes regular C++ functions anymore. They can be found via ADL. What we do instead is so much simpler and obvious to the beginner. Instead, we simply make a throwaway type that has a function call operator on it, and then we expose a context for instance thereof, so that when you invoke this function, you're actually invoking an operator overload and an object, and so we short circuit ADL completely. Now that we're happy with this formulation, we can move on to actually implementing wait for SQE in terms of it. And here we see an instantiation of stood execution completion signatures, something I referred to earlier. We instantiate it with exactly a function type which returns set value t and accepts an IOU ring SQE reference. And what this means is that the associated asynchronous operation completes only successfully, and when it does, that success is parameterized exactly by an L value reference to an IOU ring SQE. We provide a wait for SQE base type, and we derive from externally completed base with the wait for SQE signatures. And here we see the need for customizing that base type, because we want to enrich it with an intrusive linked list node, which suggests to us, of course, that we need to actually provide an intrusive linked list in our context, and so that's the last thing we do on the slide. But there's something uncomfortable on this slide. There's something that's uncomfortable to anyone who's done asynchronous programming in C++. The fact that what we yield from our asynchronous operation is a reference. This immediately takes our minds to the idea that this reference might be invalidated over the asynchronous lifetime, that this might be unsafe. And so let's think through what's actually happening here. We know that wait for SQE is an asynchronous operation. Its asynchronous lifetime extends until a matching SQE is found for it. But when that matching SQE is found, we go and we invoke a virtual function on that base class. We invoke that virtual function with that reference. But this invocation is synchronous. In the implementation of that virtual function inside of externally completed, it takes the argument it received and calls setValue on the receiver with that argument. But this is synchronous. And then inside of setValue, it calls the setValue member function of the receiver another invocation, which is synchronous. And so while wait for SQE has an asynchronous lifetime, the lifetime of that reference is only apropos in the synchronous completion thereof. But I have an even more compelling and general argument for why it is acceptable for our asynchronous operation to generate references. And that is exactly that analogy I started the talk with. If it is the case that senders and receivers are the implementation of the asynchronous equivalent of a synchronous function, then we expect senders and receivers to have all of the capabilities available to synchronous functions. And we know trivially that synchronous functions can return references, and so too, therefore, should we find this capability in the asynchronous domain. Which brings us to using the scaffolding we've set up, to actually going and implementing wait for SQE. We call externally completed, and we provide it with the signatures and the custom base type. When we perform this invocation, nothing happens. Arguments are curried, a sender is returned, everything is deferred. But later, after that sender is connected and the resulting operation state is connected, our lambda is invoked. It's invoked with a waiter which is now within its asynchronous lifetime until the operation completes. It is now incumbent upon us to glue it into that external completion modality so that the receiver contract is satisfied and the operation eventually completes. But what if we're in the happy case? What if we don't need to wait for an SQE at all because one is already available? And so we turn around and we immediately complete in this case. And this is something else that terrifies people who are used to writing asynchronous code in general, but particularly in C++. If I don't trampoline or reschedule, if I don't somehow disconnect myself from the call stack, how do I know I'm not going to blow out the stack? How do I know I'm not going to eventually segmentation fault? But think about what this would mean in terms of our analogy. It would mean that we now have a modality, inline completion, which is available to regular synchronous functions, but not asynchronous ones. But we don't need to make this argument by analogy or through principles, because think about what it would mean for the performance characteristics of our program if every asynchronous operation needed to complete out of line. It would mean that every single time you decompose a problem into several asynchronous algorithms, you incur linear cost in the size of that decomposition. And so not only is this inline completion acceptable because of the analogy we have with the synchronous domain, but it is also acceptable because if we didn't have or allow it, we would not be able to provide the performance characteristics we get in the synchronous world. We would not have the kind of zero-cost abstraction for which C++ is famous. But this is just the happy case. At some point, we're going to run into the unhappy case, and at that point, it will be incumbent upon us to publish ourselves via that linked list and do nothing further, resting assured that someone somewhere else in the system will notice that SQEs have become available and wake us up. Which finally, after a long detour, brings us back to syscall, brings us back to finally implementing that primitive we set out to so long ago. We have a sequence of asynchronous operations we want to perform. The first one waits for an SQE. Once an SQE is available, we invoke the user's prepare function therewith. Immediately thereafter, of course, we go and we consume that SQE. We publish it to the kernel, and we wait for an appropriate CQE to be posted. But in keeping with our descent through the abstraction layers, we've once again encountered a question. We have not seen the implementation of consume SQE, and so we must in turn our attention thereto. And once again, we see ourselves reaching for our old friend externally completed. The completion signatures are different this time. Instead of completing successfully with a mutable SQE reference, we complete with a const CQE reference because the completion condition is the availability of a matching CQE in C2 in the ring. And then we directly use externally completed base because, as I pointed out at the very beginning of the talk, SQEs and CQEs have a user data field. We can simply put a pointer therein and leave it to the kernel to do the bookkeeping about where to find the continuation. Now that we've set this up, we need to roll a helper function that does exactly what I just described, which accepts a continuation, gets the SQE that's about to be published, and fills in its user data with a pointer back to the continuation that will complete when a CQE which matches it is posted. Then finally, after so long, we go to the tail of the queue and we perform a single atomic increment. And in so doing, we inform the kernel that it is now available to consume this SQE. That it can now, if it notices the SQE, consume it and begin the resulting asynchronous operation. But this function returns void. This function is a helper. And we know that our asynchronous basis operations return a sender. And so we have to provide the nullary version of this function which actually does that, which calls externally completed, passes a lambda which accepts the continuation type, and just calls consume SQE thereupon to begin asynchronous execution. But the asynchronous execution we begin here is an actual bona fide Linux syscall, reified asynchronously. And think about the various things that we do with regular Linux syscalls. We might be reading from a pipe, but maybe that pipe never becomes readable. We might be trying to connect to 3 or 4 endpoints to see which one becomes available first, but a different one became available and we don't want to connect anymore. Maybe we were trying to do something and a timeout ran out and we should move on. But in the domain of stood execution, in the structured concurrency it provides, we are obligated to wait for every single asynchronous operation to complete. We can't simply allow the lifetime of an operation state to end while associated asynchronous execution is in progress. And so what this means is that we need a way to pull back that asynchronous syscall. We need a way to inform the kernel that we no longer want to make forward progress, that it is time for it to wind down so we can move on. And this functionality is available via IOU ring. IO ring op async cancel is an operation you can asynchronously submit to IOU ring and request that it cancel another outstanding asynchronous operation. You target it by providing the matching user data pointer. When we filled in that pointer, we can now cancel that operation by providing the same pointer when we submit IO ring op async cancel. And while stood execution has a rich capability to propagate stop requests, we haven't actually seen that surface in externally completed. It is a participant in the stood execution ecosystem, and so of course it can go and read a stop token from its receiver's environment. But what happens then? The whole point of externally completed is to glue in functionality that is not yet resident in the stood execution ecosystem. And so how do we inform externally completed as to the modality that it should use to cancel that in-flight operation which it has no ability to introspect because it was surfaced to it generically? And what we're discovering is that externally completed has a more complicated interface than we previously saw. We can, of course, just provide an initiation, but it also accepts a second invocable. A second invocable which allows us to inject logic as to how the operation initiated by the first invocable should be canceled. But notice the asymmetry between these two invocables. The first invocable returns nothing. It simply initiates an operation given the operation state associated therewith. But the second invocable returns something. The second invocable actually provides an operation which, if connected and started, would have the effect of canceling the main operation. What we're discovering is that what we are injecting into externally completed is not just any invocable, it is a sender factory. But this formulation, that we have some main operation in progress and now we are going to return a sender to externally completed representing another asynchronous operation, raises the specter of something interesting, something that only the asynchronous domain benefits from. Because let's think about some example. Let's think about someone who's calling consume SQE. They could be calling it in the synchronous or asynchronous domains. We might imagine that equivalent functionality is surfaced synchronously. And so we say that this is activated. It's not an asynchronous operation. It's not a synchronous function call. It's just an activation. But we've already been looking inside of consume SQE. We know that consume SQE has children. We know that it has activations nested inside of itself. We know that it defers to externally completed. But we know because externally completed is generic that it itself is not whole unto itself. It goes and shells out to children of its own. It goes and shells out to that external operation which we have provided. But we hope that at some point in time that external operation completes. It completes and gives control back to its parent activation, which is externally completed, which in turn gives control back to consume SQE, which in turn ends. And I said earlier that this can be surfaced either synchronously or asynchronously. And we know this because we call functions every single day that call a function that call a function. That's not interesting or notable. But think about what we're doing with that injected cancel sender factory. We are now providing a second source of asynchronous forward progress, which externally completed should manage in addition to the first. Externally completed now has two child activations which are making forward progress simultaneously, something that is structurally impossible in the synchronous domain because the nested activations of a synchronous function make forward progress at the exclusion of their parent. But this isn't actually that notable in the asynchronous domain of stood execution. We surface this functionality directly in the standard library with when all. You provide several senders, it starts them all and lets them make forward progress at the same time, and that asynchronous operation ends only when all of those children have completed. We see that it returns a single sender. If we want access to more complicated means of managing child activations, we have that in the standard library as well. And not only that, I've given 2 talks where I talk about functionality you could extend stood execution with to leverage this in addition to what's in the standard library. But let's go back to looking at those nested activations. Let's go back to looking at those nested activations and consider them vis-a-vis the fact that the asynchronous domain is fundamentally racy. There's no reason to believe this diagram is canonical, that it's the only ordering possible. Maybe I initiate that cancel operation to try and cancel the external operation, and the external operation happens to complete first. Because we're in an environment of structured concurrency, externally completed can only end its activation when all of its child activations have come to completion, which means that after external operation completes, it needs to wait for the cancellation. But think about the signature we gave this. We said this completes with a reference to a CQE in situ in the completion ring. But now we're being exposed to the idea that the completion of this asynchronous operation might not be the same synchronous cascade we saw earlier. Instead, we may have to wait around for that child cancel operation. And in the interim, while we are doing that, maybe that reference into the ring is invalidated. Maybe that slot is reused. And so what we are discovering is that our operation must complete by value. But if only interoperating with C APIs was this easy. If only the maintainers of the kernel were happy with a CQE that has one static size. If only they didn't give IOU ring parameters that just make CQEs bigger because you asked for them to be double the size. And if only they didn't go to that struct I showed you earlier beautiful, and perfectly amenable to being used from C++, and surface this functionality with a flexible array member. The kind of thing that makes C++ not like to interact with such a structure. And so what we're discovering is we now need to surface our own completion queue entry type, which just has all of the members we care about. As an added bonus, since we've already used user data to link up the submission to the completion, we can discard it and we can save 8 bytes. But none of this tells us how we actually implement cancel, how we actually go and fill in the body of this sender factory. But the structure here is going to be familiar. We have a sequence of operations. We wait for an SQE, and then we go ahead and we fill in all of the details needed to cancel the operation that we are targeting. Thereafter, we would go and defer to consume SQE, except consume SQE is implemented in terms of cancel, and we don't want that recursive deduction of auto, and so we simply stamp out our own consume SQE here. Then, of course, we need to reify the fact that we don't particularly care whether cancellation succeeds or fails, because if it fails, that means the operation is either not cancelable or it has already completed, both of which we are perfectly happy with. But I said earlier that std execution already has support for propagating stop requests. It does go through a stop token, which you interrogate a receiver's environment to obtain. But then we start thinking about the properties of stop sources and tokens in the standard library. We think about the fact that all of their member functions are thread safe. When you request a stop on a stop source, that is thread safe. When you ask a stop token if a stop has been requested therethrough, that is thread safe. When you construct a stop callback or destroy it, that is thread safe with respect to the invocation of the associated callback. What we are seeing in library design space is a reification of the fact that stop requests can come from anywhere in our program. They can come from an arbitrary execution agent, and therefore, for correctness, they should be handled in a way that is thread safe. But I already said earlier in the talk that the IOU ring is not thread safe. It is asynchronous, sure, but it is only safe to interact with from a single thread. But then we look at the code that we've written. When we call this factory, when we start the resulting operation on that randomly selected execution agent, which is sending a stop request to us, we go and we gratuitously interact with the ring. This is not thread safe. This is not correct. But fortunately, std execution gives us a rich, expressive, generic grammar of algorithms. We can render this thread safe at once by simply capturing the result of XX sequence and saying it starts on our scheduler. And while this formulation is interesting in and of itself, it should also bring us back to something I said earlier in the talk. When I said there was an aesthetic issue on a slide that would manifest itself consequentially later in the talk. Because what we're doing here is we are forming a sender on an arbitrary execution agent. And then we are saying that operation should be started on a particular execution agent for correctness. But think about what this would mean if any of those sender factories I interacted with were not lazy. Imagine what would happen if any of them did anything whatsoever other than curry arguments and yield senders. Imagine if any of them had the side effects that we culled from one of our sender factories earlier in the talk. It wouldn't matter what execution agent the resulting asynchronous operation ran on. We would already have a function full of potential data races. And so for this reason, because of the fact that we need this to surface the generic power of std execution, sender factories shouldn't just be lazy for aesthetic reasons, because that's consistent with the rest of std execution. They should be so for correctness reasons, because if they are not lazy, you cannot avail yourself of correctness brought through schedulers. Ruslan.
And yeah, quick question. Starts on also returns the sender, right?
Yes, starts on returns the sender. When that sender is connected and started, it will schedule onto the scheduler that's passed, and then it will call start on the operation you provided it on the execution agent associated with that scheduler. And Ruslan's question leads to another question, which is what is a scheduler, which is something that apparently Ruslan already knows. So a scheduler is the filling out of the std execution ecosystem. We've talked about senders, we've talked about receivers, and we've talked about operation states. But schedulers are the entity that fill out the ecosystem, that give us the ability to interact with execution contexts. An execution context is something that can lend to us the ability to run work on an execution agent, or perhaps one of several execution agents. And that formulation, that role that schedulers fill in our asynchronous ecosystem, suggests that the basis operation by which we submit work to them should be free of data races. And so if we open up the standard and thumb through it, we see that exactly this is guaranteed to us. The schedule function on a scheduler and all of its attendant execution is free from data races. We can call it from different threads. But once again, this leaves us in an interesting situation. We've saved cancel by going and telling it that it should schedule work on our scheduler. But that, of course, suggests to us that we have a scheduler which is not something that we have heretofore explored. And so we see ourselves enriching our IOU ring context therewith. We have to bootstrap a scheduler from nothing. Everything that you see on this slide is just boilerplate. Just boilerplate required to satisfy the scheduler concept. We use the appropriate nested type alias to say that we wish to be a scheduler. We have a constructor so we can be brought into being from a reference to our parent IOU ring context. And then we have the basis operation for which we reach for a scheduler. The schedule operation which returns a sender. And of course, schedulers can be compared to determine whether or not they are handled to the same underlying execution context. Then at the very bottom of the slide, we see the implementation of that helper function we called earlier. A helper function which allows us to get a scheduler, which is a handle to the execution context reified by this IOU ring context. With the boilerplate out of the way, we now need to put behind it actual functionality, actual code that can satisfy all of the guarantees thereof. And so for the third time in our talk, we see our good friend externally completed. Aren't we glad that we wrote a single algorithm rather than bootstrapping from nothing an asynchronous operation each and every time we reached for it? But we see that this time we complete only successfully with no parameterization. This is simply an impulse which is sent on the correct execution agent, which allows for subsequent execution to take place in the right place without data races. Then we have a schedule base type which derives from externally completed base, and we once again see an intrusive linked list hook. But because we are now dealing in a situation where we have many threads, we see an atomic intrusive linked list hook. And this formulation suggests to us that we are going to have an atomic intrusive linked list, and so we see exactly that in the body of our IOU ring context. But we see something else too. We see a new file descriptor. Because simply linking work into an intrusive atomic linked list is insufficient. We need a doorbell that we can ring to let someone know that we are waiting for them to pick us up and execute us on the appropriate execution agent. And the way we provide this functionality is through an event FD, a counter in the kernel which can be written to. We write the raw bytes of a 64-bit integer, and the kernel increments that counter by the appropriate amount. And whenever that counter is non-zero, the file descriptor becomes readable. We can read from it the 8 bytes of that integer and reset the counter. And so we see now what needs to happen. We ring the doorbell by writing to the event FD. The other side becomes aware we've rung the doorbell by reading from the event FD, and then it knows to go toward the queue and drain it. All that remains is to back up these words with code, to go out again to externally completed, to provide the needful template arguments, and then to link it into the intrusive linked list. The sharp-eyed among you might notice that this linking into the intrusive linked list has an instant in which the intrusive linked list is inconsistent, in which you cannot reach the tail node internally from the list's next pointers. But don't worry about that. We're going to deal with that inconsistency on the consumer side. We have a way to mediate that problem, which we're going to discover in just a few minutes. Now that we're published through the intrusive linked list, of course, we need to go and ring the doorbell. And so we have an unsigned 64-bit integer that is 1. And we write it to the event FD, thereby ringing the doorbell. Unfortunately, this is one time in which I'm going to actually write a synchronous syscall. Because we don't know we're on the correct thread to interact with the IOU ring, we need to fall back and make an expensive syscall. We can take solace in the fact that this should be a rarely performed operation, one which we want to avoid. But as we look at the code on the slide, as we think about all the code we've seen heretofore, we realize something. We realize that we have run out of code we haven't seen the implementation of. But then we think about what we've been doing for the entire talk. We went and we waited for SQEs by linking ourselves into an intrusive linked list. And I said at the time, someone else is going to notice that you're waiting and then wake you up. But we haven't seen anybody waking us up. And then we went and we submitted an SQE to the kernel with a user data token that points back to our continuation, but we never went and actually read any CQEs from the kernel. And then we went and we dropped off scheduled work in an atomic intrusive linked list and rang the doorbell, hoping that some other side would wake up and invoke us on the correct thread. But we didn't see the implementation of that either. Because what we've done is we've set up a vast amount of forward progress to be made, but we haven't actually provided any locus to actually make that forward progress. And so what we're discovering is that there's a completely independent API on our IOU ring context that we now need to reify, that we now need to fill in with code. We need to provide it with a run function by which a caller can delegate an execution agent to make that forward progress on this IOU ring context. But this formulation, this idea that we are delegating an execution agent to the IOU ring context raises an interesting question. What is the duration of that delegation? How long are we delegating the current thread to the IOU ring context? And the obvious answer is that we are performing that delegation until all of the work is completed. But that raises the question of what does that mean? What does it mean for all of the work to have been completed? How can you tell? And another naive answer might be, well, we will keep a reference count inside of the IOU ring context. When you submit work, we increment it. When work completes, we decrement it. And then when that counter reaches 0, we are done. But that supposes that our IOU ring context is the only execution context making forward progress anywhere in the program. What if our caller submits work to the IOU ring context, which uses the IOU ring context to make some syscalls and then goes off and executes some work somewhere else? After that work executes somewhere else, they want to return and use the IOU ring context again, but that reference count dropped to 0. The run function returned, and the IOU ring context is no longer able to make forward progress. What we are discovering in this analysis is that the definition of work being done can only be imposed upon us by the caller who actually defines that work. We need some way for them to inject intelligence into us as to when that delegation should end. And that is exactly why we receive a stop token. We receive a stop token so our caller can let us know when they are finished using this IOU ring, when the higher level application logic that only they are aware of determines the IOU ring context is no longer needed, that forward progress can stop, that the execution agent delegation can end. Which brings us to filling in this function. Filling in this function by first going and writing the top of the function. The top of the function and the bottom of the function are going to be completely separate because the top has a special property. We have a Boolean to record whether or not we are done, and then we go and we connect a run scheduled operation sender piped into std execution then to a null receiver that simply ignores the result thereof. And we should consider what this means. We are discovering another sender factory that gives us a locus of asynchronous execution, which apparently runs some scheduled operations. But based on the fact we attach a continuation and provide it with a stop token, we can gather that asynchronous operation completes at some point. Once it completes, we want to mark our local variable done as true. But we get back this operation state as a local variable in a synchronous function, and then we go and we call std execution start thereupon. What we are doing is we are starting to make asynchronous forward progress using an operation state which is embedded inside of a regular synchronous function. And this means two interesting things. The first thing it means is that we have implemented that pattern from earlier wherein an activation has multiple children. Because the bottom part of this function is going to run. It's going to run, and so is this asynchronous operation together. Which brings us to the second interesting thing here. I said earlier that you're not allowed to just destroy an operation state while the associated asynchronous forward progress is being made. You need to wait for it to complete. But we already know what this asynchronous operation does when it completes. It goes and it sets done to true, and so what we've gathered is that the bottom part of the function can't return until it sees that done is true either, because otherwise it would destroy the operation state while asynchronous forward progress was being made. And so as we unveil the bottom part of the function, we are unsurprised to find exactly this formulation. We loop until we see that done is true. And on every iteration we go and we enter the kernel. We enter the kernel, come back, and we complete all the pending CQEs. Then we go and we initiate all the operations which are pending, waiting for an SQE to become available. But there are several things on this slide whose implementation we have not seen. But before we go on that journey, I want to draw your attention to something of critical importance. This parameter to IOU ring enter determines whether IOU ring enter will not return until a certain number of completions have been accomplished. You can say 5, for example, and the kernel will keep your thread until it has published 5 completions to you. But you can see that I pass 0 or 1 conditionally. Conditionally on there being a wait for SQE head. Because think about what it would mean if I entered the kernel with someone waiting for an SQE to become available, but told the kernel not to return to me until it has 1 completion. That would mean the kernel would drain the SQE ring, making a large number of entries available for consumption, but then occupy the thread until it could complete one of those operations, starving one of the pending operations, waiting for an SQE that just became available. And so in this case, we tell the kernel we don't want to wait for any completions. We want it to drain the submission ring. We want it to return control to us so we can wake up all of those waiting tasks. But if we don't have any waiting tasks, we don't want to hot spin the CPU repeatedly entering the kernel, and so we provide 1. We say to the kernel, you can put this thread to sleep until there is actual work for us to do. Which brings us to those 3 things we haven't investigated yet. Those 3 functions we have to now descend into in order to see the totality of the implementation of our IOU ring context. And so we'll start with the synchronous ones. We'll start with the synchronous ones to give our brains a bit of a rest from considering the asynchronous domain. Here we want to drive all of the pending completions through to completion. And so we see that we loop infinitely. We loop infinitely until there's no more work to do. And the work we do, of course, is we go and we load the head and the tail of the completion ring. And if they are equal, the ring is empty. There's no pending completions, and so we simply return. On the other hand, if they are not empty, there is at least 1 completion queue entry herein. A completion queue entry herein that indicates the completion of an outstanding asynchronous operation, one which we are obligated to deliver. And so we go and we resynthesize that continuation pointer. We go by synthesizing it by performing some pointer arithmetic on the linear version of the ring. We take the head and tail pointer, we realize them as a linear index, and we get that pointer. But then we grab the user data therefrom. We grab the user data therefrom, and we know from the other side of the protocol that is a pointer to a continuation object, one being managed by externally completed. And so we complete it, telling it the operation was successful, and passing that version of a CQE that we provide, that version of the CQE we provide to work around the fact the kernel allows the structure to have a variable length. Thereafter, we do one more critical thing before we move on. We, of course, go to the kernel and tell it we are done with this CQE, that it doesn't need to keep the CQE available for us anymore, that it can use it to publish subsequent completions. Which brings us to that other synchronous function, waking up everyone who was waiting to initiate an operation, waiting for an SQE to become available in the submission ring. And so the first thing we do is we check to see if anyone's waiting at all. If they're not waiting, there's no work to be done, and so we return. But if they are waiting, now we need to get them a submission queue entry. But we know that's something that can be impossible. We know the ring can be full, and so we perform get SQE, and then we check that pointer. If the pointer is null, the submission ring is full, and so we return. Our waiter will have to just stay asleep. Otherwise, there is now the ability to complete that waiting operation, to go and pass that SQE through to the waiting operation, but only after we unlink it from the intrusive linked list. What we are doing here by completing it is we are telling it that we are done with that operation state, that it is perfectly free to destroy that operation state, and so we need to keep our promise by making sure we are done with it before we dispatch the completion. If we were to move this unlinking to after complete, then we might run into a situation where calling complete destroys the operation state and renders that unlinking undefined behavior. Which brings us to the most daunting asynchronous operation in the talk, the implementation of run scheduled operations. The other side of our scheduler, which goes and picks up scheduled work and dispatches it on the correct execution context. That execution context being, of course, our IOU ring context. And in order to understand this function, we really need to work through it from the outside in, because we have return of just piped into let value. But this isn't just like we saw it earlier with no arguments. It's just with a value initialized 64-bit integer and a Boolean whose value is false. This takes those values and sends them down the asynchronous pipeline when it begins. It sends them to let value. Let value stores both of those values in its operation state and then invokes the invocable it's provided with. But think about what this formulation means. We take that 64-bit integer and that Boolean and we store it in let value's operation state, which means those references are now valid for the asynchronous lifetime of the asynchronous operation. We don't need to worry about them being invalidated as long as we respect the structure of structured concurrency. We know that inside of this activation frame that is inside these braces, we can rely on them being valid not just for its synchronous invocation, but also for the associated asynchronous lifetime. Because we return a sender which let value connects and starts. Let value doesn't complete until that sender completes, and so our integer and Boolean are within their lifetime for everything we are going to do inside of here. And what we're going to do inside of here is have a stop and dispatch operation. One which is concerned with the stop token and its stop request, and one which is concerned with actually dispatching those scheduled operations. But then we go and we combine them together with when all and return them. Whoever obtains the sender, when they connect and start that sender, will connect and start both of those operations transparently. Run them both through until both of them are completed. Which of course raises the transitive question how those are implemented. And so let's think about what it is that stop needs to do. Stop needs to complete when a stop request is made, and so we're going to use an extension algorithm called never. An algorithm which never completes successfully, which never completes in error, which only completes with set stopped when a stop is requested. But when a stop is requested, we want to trigger graceful shutdown. This is not an unusual situation for us, and so we simply use upon stop to transform that into a value completion. But notice the stop token is provided as a parameter. We used unstoppable earlier when we provided the senders through to when all. We need to inject a stop token into the environment in which never runs, or never will never complete in any way whatsoever. And so we go and we write that stop token through to its environment. We ensure that it can receive that impulse when it should come to an end. But think about what we're doing here. We're attaching a stop callback to a stop token, and then we're completing when a stop request is issued. But we know from earlier that stop requests can come from arbitrary execution agents, that they do not have to be delivered thread safely. And so if we want to go and interact with anything which also interacts with our IOU ring context, we need to make sure that we transition that impulse onto the correct execution agent. And so we simply use an algorithm that does that. We say that our operation continues on the appropriate scheduler. Now that we've figured out where to run this operation, we can perform what we actually want to do, which is set stop dispatch to true. But think about the interaction of these two things. In order for thread safety, in order for correctness, we need to schedule onto our own execution context. But we know what that does. That rings the doorbell and links us into an intrusive linked list. But immediately upon the point where we're dispatched, we set this Boolean to true. We set this Boolean to true, but we know that we're only being invoked because we rang the doorbell and the other side is now awake. So not only do we wake the other side up, we left behind evidence for them that they should stop making forward progress. We left behind a binding constraint on the implementation of dispatch, which we're now going to look at. And of course, dispatch is going to contain an asynchronous loop. We want to dispatch all of the scheduled operations, not just the first ones we receive. And so we reach for the extension algorithm repeat until, which repeats an asynchronous operation over and over and over again until it sends true. But what is it that we want to do? We want to wait for the doorbell to be rung. We want to read from the event FD, and we know full well how to do this in the asynchronous domain with IOU ring. We just want to make an asynchronous read syscall. An asynchronous read syscall against our event FD, reading into the raw bytes of that 64-bit integer. Once this completes, we can go and we can dispatch all the pending operations and then return true if and only if the other side tells us that all of the outstanding work is done. But that simply leaves the implementation of dispatch. An implementation which is quite daunting. An implementation which is excessively concerned with atomics, which are not the topic of this talk. But if we make the implementation fill the slide even more, by looking at the version that's in my repo filled with comments, we do see something that is apropos to us, that answers the question of why it is that dispatch needs the integer we read from the event FD. Given we have a thread-safe atomic intrusive linked list, why can't we just eagerly consume all of the work? And the answer is in this comment. The answer is in a comment that I can, of course, make bigger so everyone can read it. And the answer to that question is this scenario. Imagine you have someone who's trying to schedule an operation. They go and they link themselves into the intrusive linked list. They are now published and available for consumption there through. But of course, we know they need to ring the doorbell. But as they go to ring the doorbell, the kernel decides that it doesn't want to schedule them anymore. It puts them to sleep. The kernel schedules some other thread to run. Perhaps the thread that is running our IOU ring context. And maybe someone else scheduled work to run as well. And so we wake up and we read one from the event FD. But under the formulation wherein dispatch is greedy, we would dispatch 2 completions and not 1 because we would see that half-published scheduled operation. But now imagine that dispatching both those operations completes all of the work our caller wants to do. Our caller thinks the IOU ring context has fulfilled its useful purpose and requests a stop through the stop token. This would then cause us to return out of run. Our caller would have no reason to believe anyone is depending on the IOU ring context. They will be well within their rights to destroy it. But then at this most inopportune moment, imagine the kernel decides it wants to run that thread we were talking about all the way at the beginning of this formulation once again. It wants to give that thread the ability to make forward progress. Forward progress which will be immediately writing to an event FD that has been closed, whose numerical value is stored in an object whose lifetime has ended. Undefined behavior which causes us to require this formulation, that we only dispatch the number of scheduled completions which have been fully published to us through writes to the event FD. And having reviewed this, we've actually designed ourselves an IOU ring context. But we haven't just designed the IOU ring context, we've actually gone through and we have implemented the entire thing, considered all of the edge cases in all of the functions, and solved all of them. We now have, through idiomatic cplusplus26, access to every single asynchronous syscall that is supported by IOU ring. But is that the takeaway from this talk? That IOU ring is cool, that it allows you to make asynchronous syscalls, and that now we have idiomatic C++ that allows us to leverage and surface that functionality? I would say no. Because think about what we did in this talk. We started with a high-level API, read sum, and we modeled it as a sender. And then we descended through the abstraction layer all the way to the bottom, right next to the kernel. But every time we did this, we found staring back at us another sender. Because what we did in this talk is we bore out that analogy. The analogy that senders are the asynchronous analog of a regular synchronous function. Because if when you are implementing low-level functionality, you will reach for a synchronous function, which I'm sure you will, then it should also be the case that when you are implementing low-level asynchronous functionality, you will therein reach for senders too. Matt and then Vito.
So there was a spot where you make a blind call to write on the event FD and don't check the return value of it. Is there something that guarantees that write call will succeed?
So the overwhelming, traumatically vast majority of writes to event FDs will succeed. I think there are narrow edge cases in which they can't. I actually have, so there's another problem in that same vein in the talk, which is that I assume that IOU ring enter always succeeds. And I may or may not do it, but I have an idea for a lightning talk that's about that. Because the issue you run into when you suppose that these things can fail is that when you do the full analogy and projection, you realize that user data in the SQE is a return address, right? And event FD is essentially you saying return from a function, right? When you fully bear out the analogy. And so the idea that these really critical syscalls that have these extremely obscure failure modalities can fail is basically saying when you call a function, jumping through the return address pointer can fail, right? There's no way you can't reason about what that means, because every time you try and do it, you end up belying one of the requirements of structured concurrency, right? I failed to wake up an operation. I don't know which operation I failed to wake up, right? How do I know, right, which ones are never going to complete, which ones are going to complete? And how do I do that generically? So this is a problem, and there's actually there's a much simpler implementation of the scheduler, which uses, so when a long time ago, kernel series 5, we gained the ability in IOU ring to do an asynchronous operation that posts a blind completion to another IOU ring. And since, I think it's kernel 6, that's surfaced through a regular synchronous function. So you can call a function and pass it the file descriptor of a ring and say, wake this ring up with this completion. And it's really tempting to use that instead of all this complicated stuff because it allows you to avoid the intrusive linked list, it allows you to avoid the event FD. But when you actually go into the kernel source and you look at that syscall, that syscall can like trivially fail. And so all this stuff is basically trying to bootstrap on the most fail-safe primitives we have, right? Because eventfd, the modal failure from a read or write to an eventfd file descriptor is that you pass a size other than 8, right? Like if you try and read with the size of 7, the kernel will be like, what are you doing? And so that's the modal way in which it fails. Almost every other pathway in there will succeed, and it's especially far more resilient than the ring signaling, because the ring signaling can fail for a bunch of esoteric reasons, right? Like it'll try and push something into the other ring's completion queue, but the completion queue might be full, right? If the completion queue is full, right, then it needs to allocate memory for this overflow buffer that it can store that completion queue, but the allocation could fail. And the reason why we can avoid it by adding the complexity in the user space side is that we don't need to allocate a space because we have space in the operation state. We do that allocation when we set out to perform the operation. Once we're at the point where the operation's in flight, that's already been allocated. That kind of like closes the circle, and that's why operation states are so powerful, is because they upfront a lot of allocation that is done lazily in other asynchronous frameworks. And so you could do things like say, this asynchronous operation does not have a failure modality because it doesn't allocate, right? Which in a lot of other asynchronous frameworks, you just can't say that. Every asynchronous operation can fail with bad alloc. Vito?
So I might have just missed it. Nominally, I should just be able to schedule basically any operation state on your scheduler, but we very heavily focused on stuff that's actually going to submit an SQE and produce a CQE. Was there something in there that I missed that was like, at least in studexec's version of IOU ring, I think it has like a ready call that says, actually, I'm just a regular asynchronous function, just bounce me to the completion queue and invoke me next time you come around the event loop.
Wait, sorry, which, this is...
In studexec's version of IOU ring.
Oh, I haven't
Okay.
I haven't looked
So
at that.
here's a question. So like you just call schedule, right?
Mhm.
And you get a sender, which
Yeah.
you can then, which doesn't actually involve submitting an SQE. Because I
Yeah.
just want, so how does that work with your implementation? Is there something that just short circuits through and doesn't submit an SQE?
When you're, sorry, it doesn't submit you when you're on the right context, or?
Yeah, when you're on your IO context.
It does not do that, no.
Okay.
Yeah, I leave that for the user to figure out or for a future improvement.
Okay.
But like the whole thing about, using it to submit SQEs, if you go, where is it? Here, this is a schedule operation that does not end in submitting an SQE.
Got it.
Yeah, because like all it does is it wakes up in the right context and then just sets a Boolean to true.
Okay, I understand.
Yeah. I saw a hand here and then Jody in the back.
I forget which slide, but there was one where you were like looping like a while not done.
Yeah, that's
was that a
this
like
one.
how is it not a race?
No, it was an earlier
It
one.
was an earlier one.
Wait, loop it. Oh, you mean like an actual synchronous loop?
Stop. Yeah, it's the stop
It's this.
token.
Is this one or the previous one?
Further back.
So it's the CQE one.
Further back.
Further back.
With then there's this.
No.
Yes, this
Yeah.
one. You have this.
Yeah,
You have
yeah,
the stop
the while-
token
the
while
while-
not done.
Yeah. What's racy about that?
It's a Boolean done.
Yeah.
The done is set inside the scheduled operation, and you're waiting for it.
Right. And so in general, if I didn't know anything about run scheduled operations, in general, this would be a data race, right? I'm mutating something that is not atomic, and I'm also reading from it. But if you go through to here, you can see inside stop, right? So kind of famously, like this has become a source of a bunch of people complaining on NVIDIA studexec issues list. When all completes on whatever execution agent the last operation to complete completed on, right? So this when all operation can complete on either the execution agent which completes stop or the one which completes dispatch. Does that make sense?
Okay.
So let's look at the one stop completes on. Stop schedules onto us, and so it completes on us. So there's no race if it completes there. This here, right, is an actual syscall that completes on our context, so it completes on us, and so there's no race, right? Only because these asynchronous operations that we're initiating have the special property that they always initiate on. Effectively, if you go back here, all this stuff, like once you peel back the abstraction and think about what's actually going on, all of them complete inside of complete.
Okay.
Right, so inside of complete, we pull out a CQE, we do the cast, and we complete it, and then they all complete in there. Right, so they complete in there, and they write to done, which is above them on the synchronous stack frame.
Okay,
so it's
thanks.
bed safe. Jody.
But you understand how unobvious it is.
Yes. No, there's this operation here has exactly 0 obvious components. Jody.
Yeah, so I appreciate this because I have a much better understanding of how things work underneath. But as you said, one of the things, the point wasn't necessarily IOU ring.
Yeah.
But So let's say I wanted to implement this with another way of ringing the doorbell and dispatching my asynchronous event back to me, and I wanted to use senders receivers on top of them. So for example, take Michael Maniscalco's signal trees, which he's talked about a few times, but it's basically just another way of being able to have these asynchronous events being able to be dispatched to some function that gets called. How would I wrap something else? I mean, and you may not know how signal trees work, but I'm looking for the regular, what's the thought process that I have to go through in order to wrap some other asynchronous mechanism with senders and receivers?
Yeah, so I think that the analogy that I give that I consider to be the thrust of the talk is how I start to think about these things, right? Like when you want to arrayify anything as in stud execution, as a sender and receiver, you have to start looking for the asynchronous function call and the asynchronous return, right? And as long as you can find those two things, you can adapt it to stud execution. Like a stud execution is a very generic framework that you can bootstrap on top of anything that models the idea of structured concurrency. So as long as you can provide it with something that satisfies those guarantees, that has this structure of like asynchronous call and then asynchronous return, you can adapt it to stud execution. As to how it is that you should actually take your external APIs and glue them into stud execution, Dietmar will talk about that later in the week. So I'm sure he'll dispense with wisdom there. I've done it in this talk on top of IOU ring and the talk in Core C++ in 2024 on top of ePOL. But that's not by no means the limit, right? There's people who like to bootstrap this on top of on GPUs, for example. Yeah.
You do need guaranteed completion, though.
Yes. Yeah. So I guess there's shotgun mics, but the guaranteed completion element is like one of the hardest things to provide. And the talk I gave at CPCon last year dives way into that, because it basically takes and tries to say, what if you want to take ASIO, which famously is a model that does not require completion, and you want to glue it into stud execution. And like most of the content of that talk is how exactly do we glue guaranteed completion, which stud execution requires, on top of something that fundamentally is designed in a way that's at odds with that does not provide you with that at all. But that gets to the answer to Matt's question, right? Which is that an asynchronous operation that never completes is like a function that never returns, right? It doesn't make, you can write it, but it doesn't make any sense, and you can't reason about an ecosystem that involves it.
Yes, so one of the patterns, as I understood it, was we have a not thread safe resource. So each time in our async stuff, we have to make sure when we access this resource that we are back on this single threaded scheduler that has the access.
Yes.
And this seems to me now that this pattern is still heavily complexly intertwined with the actual syscall stuff. Can this probably further be also decoupled as a generic pattern, depending on what
I'm trying to figure out exactly what you're poking at here, right? Because you do have to be on the IOU ring context, meaning you're running on its delegated execution agent to access it. But we do provide the escape hatch, and if you're somewhere else, the algorithms of stud execution make it extremely easy to say, go on this context, do this thing, go back.
Yeah, so it's just this primitive of, I have the scheduler and I always have to make sure to get back to that.
Yes, and there's a lot of conversation that's gone on about algorithms that can provide those kinds of guarantees. If you look at Affine, right, which is part of the implementation of stud execution task, it tries to provide that guarantee that it will always run the code that's visible to you on a single execution context. I don't use that here because there's like a cross-cutting concern, right? Like if someone wants to use this IOU ring context and they know their whole application is single-threaded, which is a very interesting full-featured class of applications, ones that have one thread. There's no reason for them to ever pay for any of the checking or the compilation time complexity of making sure they're on the right context, because there's only one context, right? And if you want to write very low-level operations, you want to divorce yourself from that cost too. Whereas if you want to write code and you don't want to worry too much, and you want to make sure it's always correct, then you can reach for Affine or you can reach for stud execution task in order to do that. Any other questions?
So, forgive me if this sounds a little bit naive. It's like C++ seems to have like 3 kind of related async stuff with future and coroutines and senders receivers.
People should pretend that futures do not exist.
And how about and coroutines with this one?
So coroutines are interesting because there's a coroutine story that sits on top of stud execution. You can, if you're writing a coroutine, you can pick a promise type that derives from as awaitable senders, and then senders become awaitable in that coroutine, right? So you can then co-await on a sender.
So when designing an API, at the API level, you should design for senders and receivers and not for coroutines.
That's been the topic of several discussions that we've had in Library Evolution. One of the reasons why I think that you should design for senders and then adapt later to coroutines is because it's not pointed out in this talk, or maybe even the next part of this talk, but it will be pointed out in my lightning talk, that senders have a far richer completion vocabulary than coroutines do, because coroutines are like, they try to be as similar to a regular function as they can be, and regular functions have a bunch of limitations that are apropos here, which is that they have to complete successfully in exactly one way. When they do so, they have to send 0 or 1 values. They can only send one type of error, which is an exception, and they can't send set stopped, right? Senders have none of those restraints. They can complete successfully in 0 ways or an infinite number of ways. They can send any number of things they want. They can complete with errors with things that aren't exceptions, and they can send set stopped. Casper, you had something to say about coroutines.
I had something to say about something else, but I do have something to say.
Okay,
about
we'll go for it. Yeah.
If you start with sender receiver, it is fairly trivial to make your algorithms non-allocating by default. With coroutines, you're at the mercy of halo optimizations, which barely ever work. So if you want your libraries to be consumed in real-time contexts and real-time safe in, kind of trivially, write it sender receiver first. I wanted to ask you about your run API.
Yeah, we can go back to that's on the screen just so
Because
everyone reminded. Yeah.
One issue in a world where you are forced to only have one thread but multiple execution contexts it has to serve. The stop token seems to me like it's not sufficient because you don't have a run sum.
So this does not
interface.
have a run sum, and I know that I think it was Lewis, Kirk, and someone else did some work on the idea of like execution contexts it could share. I haven't given much thought because I don't typically run into use cases that have that. You could conceive of a world where you do that, especially with, it's not covered in this talk, it's alluded to at the beginning of the next talk and at the end. IOU ring supports running in what's called submission queue polling mode, which is where the kernel spins up a thread and hot polls the submission queue, and then you never perform any syscalls ever, even enter. So it would be trivial to share the context then, right? Because you just check and then you're like, someone else can run. But here you need to enter the kernel, and so the question becomes, who's the one who blocks until, like, to avoid hot spinning the CPU? When you're hot spinning the CPU, it's trivial to share, right? You're just like, okay, you check, now you check, you check. So I haven't given much thought to that. I know some people have. I don't understand their ideas quite yet, but I haven't tried to engage with them that deeply.
I mean, it's basically just turning this while into an async while.
Right, but this while, right?
Yeah.
Turning this while into an async while doesn't help because this is synchronous.
Yeah, you need the ringing the doorbell to be a forward signal.
Oh yeah, yeah. You need to add a new like.
And then
ring
it
doorbell.
wakes up the thing that actually runs the thing, and then you can multiplex various run loops on the same thing.
Yeah, so that's something I have not given any
Yeah.
consideration to because I've never run. I personally, I'm not saying no one has this use case. My use cases never have included wanting to share a single thread. I have no doubt those use cases exist because like Lewis, Kirk, and I think someone else gave it serious thought, but it's never cropped up. So for me.
I have done that because we needed to do this and Redis, and it has its own ideas of how it's.
Oh, wonderful.
Yeah.
I have 90 seconds.
I didn't catch
Someone
the
else.
second word. You've done this and
Oh,
Ben.
Redis
Can
is
you
a
show,
is a
stop
Redis
Show which?
interaction
Stop.
library.
The implementation of stop.
Yeah.
Because it struck me as rather sort of infelicitous that you have to, like, there seems to be an asymmetry here. We can do everything on 3 channels except for schedulers. Which
Well, I
is
mean,
why you have to handle upon stop and then go onto another scheduler. But that scheduler has to complete on the value channel, so you can't.
Yeah, you could conceive of, so if I'm remembering this correctly, continues on only intercepts and redirects
Right.
the value channel.
Right.
You could conceive of a continues on that doesn't do that, right? And then you could conceive that then if you had that,
you
at the
could-
bottom, I wouldn't have stood execution then, I have stood execution upon stopped,
Right.
right? But the problem with that then, right, the other issue you run into, if you compose that, is that if you have that upon, no, that actually would work, because upon stop will return,
Compose on value channel.
yeah, we'll go to value, because the problem with sending stop from stop is that then it makes when all do weird things.
Right.
Which I want to avoid. But you're right. Like if continues on intercepted stop completions and rescheduled those, then I could use upon stopped and I could avoid that upon stopped, like just change it to the value channel detritus. Yeah. Jody.
Is that when all thing you talked about earlier the specification or an implementation quality?
So when all waits for all its children to complete, and if any of its children ever tell it they can't complete successfully, they send stopped or error. When all realizes it can't satisfy its contract of all the children completing successfully, and so it stops all the remaining children, right? So if you had stop that sent stopped, right, you could conceive of a universe wherein when all would try and stop dispatch, and then would end with stopped. But if it ended with stopped, and you went back here, right, runs that then only runs on the value completion, so you'd never set done, so you would hang, right? You could change that to upon stop too, right? But then you have run scheduled operations that have two completions, stopped and the value would never fire, instead of having just one, which makes sense in this context, so we know it always completes, in the moral equivalent of successfully. So I think that's the end of the slot. So I'll see those of you who want to see the next part in 30 minutes. Thank you so much.
Robert.